John Wheeler called me once. Well, he called a lot of people, and he said something I couldn't shake for 20 years. What if there's only one electron and it's just very, very busy? Now, Wheeler was not a man you dismissed. Wheeler was the man who gave us the term black hole. Wheeler was the man who sat across from Einstein at Princeton and argued with him face to face about whether quantum mechanics was complete. Wheeler was the man who trained Richard Feynman. And if you know anything about Feynman, you know that training Feynman is not a small thing. So when Wheeler says something that sounds insane, you don't laugh, you go home, you think about it for 2 decades, and then eventually you either decide he was wrong or you decide the universe is stranger than you were prepared for. I have not yet decided. That's why I'm standing here. But let me back up. Because before I can tell you what Wheeler was talking about, I have to tell you something about electrons that most people walk past without stopping. And the thing I have to tell you is this. Every electron in the observable universe, all 10 to the 80 of them, give or take, is absolutely, perfectly, completely identical. Not similar, not nearly the same, not the same with an experimental error. Identical. Same mass, same charge, same magnetic moment, same spin. Same in every measurable way that physics has ever devised a way to measure. You take an electron from a hydrogen atom sitting in a lab in Stanford, California, and you compare it to an electron from a hydrogen atom sitting in a galaxy 12 billion light years away, and you will not find a single difference. Not one. The electron does not have a serial number. It does not carry a history. It does not age. It does not wear out. Every electron is every other electron and has been since the beginning of time. Now I want you to stop and ask yourself, why? Why should that be true? Because it is not obvious. It is not something you could have predicted just by sitting in a chair and thinking about it. There is no law written on the wall of the universe that says all the fundamental particles of a given type must be perfectly identical. You could imagine a universe, it's a perfectly coherent universe, mathematically speaking, where electrons come in slightly different flavors, where the electron that spent the last billion years inside a red dwarf star is a little different from the one that's been drifting through intergalactic space since the Big Bang. You could imagine that, but that is not the universe we live in. In our universe, they are all the same. And that sameness is so precise, so absolute, so unbroken across the entire history of the cosmos that it demands an explanation, or at the very least, it demands that you feel the weight of needing one. Most physicists, when pressed on this, will tell you that the identical nature of electrons follows from quantum field theory, and they are right. In quantum field theory, you don't think of electrons as individual particles bouncing around. You think of them as excitations of a single underlying field, the electron field that permeates all of space and time. An electron isn't a thing that exists and moves. An electron is a ripple in a field. And every ripple in a given field has the same properties because it's the same field. That's why they're all identical. The field is the thing. The particles are just what the field is doing in a particular place at a particular time. That's a satisfying answer. It has mathematical precision behind it. It works. And yet, and I say this as someone who has spent decades working inside quantum field theory, it leaves something unsaid. It tells you the mechanism. It doesn't tell you why the mechanism works the way it does. It doesn't tell you why the field has the properties it has and not some other properties. It doesn't tell you why there is one electron field and not 47 slightly different electron fields that produce electrons that are almost but not quite identical. Quantum field theory describes the universe. It does not explain it. That distinction matters, and the day you stop caring about that distinction is the day you stop doing fundamental physics and start doing engineering. So we have this fact-perfect identity, and we have a description of the fact. And somewhere between those two things, Wheeler had an idea. Here is where it gets strange. Wheeler's idea was this. The reason all electrons are identical is that they are, in literal fact, the same electron. One electron, singular, moving through space and time in such a way that it appears, from our vantage point, to be everywhere at once. And the reason it appears everywhere at once is that everywhere at once is exactly what a single particle looks like when it's weaving back and forth through time, forward into the future, backward into the past, crisscrossing itself again and again until what you're looking at is not a single trajectory, but a kind of cosmic tangle that, from any given moment in time, looks like a nearly infinite number of particles sitting side by side. Wheeler didn't keep this idea to himself. He told Feynman, and Feynman, who was Wheeler's graduate student at the time, and who was even then already one of the sharpest minds in the room, took the idea and did what Feynman always did. He checked it. He turned it over. He looked at it from every angle. He found what was beautiful about it, and he found what was wrong with it. And then he told Wheeler what was wrong with it, and Wheeler, who was a great enough physicist to take that kind of correction from a graduate student, listened. What Feynman pointed out was this: if a single electron is weaving back and forth through time, then every time the electron moves backward in time, it behaves like an anti-electron, what we call a positron. A positron is the antimatter counterpart of an electron. Same mass, opposite charge, and they annihilate each other when they meet. Now, a single electron weaving through time would produce, at any given moment, roughly equal numbers of forward-moving segments, electrons, and backward-moving segments, positrons, which means if Wheeler's picture is right, there should be approximately as many positrons in the universe as there are electrons, and there are not. There are, as far as anyone has been able to measure, vastly more electrons than positrons. The universe is almost entirely made of matter, not antimatter. That asymmetry is one of the deep unsolved problems in cosmology, and it sits directly in the path of Wheeler's one-electron universe. Feynman told Wheeler this. Wheeler, to his credit, said something like, maybe the extra positrons are hidden inside protons. This was not a satisfying answer. It was a holding maneuver, a placeholder, the kind of thing you say when you're not ready to abandon a beautiful idea, but you can't yet answer the hard question. I've done it myself, more times than I'd like to admit. You hold on to the beautiful thing and you keep working, hoping the hard question will eventually yield. Sometimes it does. Sometimes the beautiful idea turns out to be right in ways you didn't initially understand. Sometimes it turns out to be wrong in exactly the ways that were pointed out to you 30 years earlier. Physics is not a linear process. It is a messy, recursive, humbling process, and anyone who tells you otherwise has either never done it or is selling you something. So where does that leave us? We have a beautiful idea, one electron, threading through time that has a serious empirical problem. That problem is real. I'm not going to wave it away. But I want to argue that the idea, even if it is not literally true in the way Wheeler imagined it, is pointing at something that is true, that the intuition behind it is sound, even if the specific implementation is flawed. And to make that argument, I need to tell you about the mathematics that Wheeler was, whether he knew it or not, reaching toward. Let me build something from the ground up. Stay with me here, because this part matters. In 1928, Paul Dirac wrote down what is probably the most beautiful equation in the history of physics. I say that knowing that there are people in this room who will argue for Maxwell's equations, or for Einstein's field equations, or for Schrodinger's equation, and those are all extraordinary, but the Dirac equation is something else. It is the equation that describes how an electron moves a relativistic equation, meaning it respects the rules of special relativity, and what Dirac found when he solved it was that it didn't just describe electrons, it described something else. It predicted the existence of something with the same mass as an electron, but with opposite charge. It predicted the positron before anyone had ever seen one. Carl Anderson found the positron in cosmic ray experiments in 1932, 4 years after Dirac wrote down the equation. That is what a good physical theory looks like. It doesn't just describe what you already know. It tells you what's there before you've looked. Now here is what the Dirac equation is actually doing that matters for us. When Dirac wrote down his equation, He was trying to reconcile quantum mechanics with special relativity. And to do that, to write a wave equation for an electron that satisfied Lorentz invariance, he found that the equation naturally mixed together what we would call particle states and antiparticle states. They were not separate things in the mathematics. They were two sides of the same solution. The electron and the positron were not two different objects that happened to have related properties. There were two aspects of a single mathematical object: a spinor, which is a mathematical structure that transforms in a particular way under rotations and Lorentz boosts. The electron and the positron are, in a deep mathematical sense, the same thing, just with different orientations in an abstract space that we call spinor space. This is not metaphor, this is not poetry, this is mathematics. And now I want to connect this to Feynman, because Feynman took Dirac's mathematics and did something extraordinary with it. What Feynman realized, and this is the insight that eventually became the foundation of quantum electrodynamics, which is the most precisely tested theory in the history of science, is that you can describe an electron moving forward in time and a positron moving forward in time as two different interpretations of the same underlying mathematical path. A positron moving forward in time is mathematically identical to an electron moving backward in time. Not physically identical, I want to be careful here, but computationally, mathematically, for the purpose of calculating what happens in a given interaction, you can treat them as the same thing with a different time direction. Feynman used this to simplify his famous diagrams. It's why in a Feynman diagram, you draw an electron line with an arrow on it, and when that arrow points backward in time, it represents a positron. Same line, same particle, different direction. This is Wheeler's one electron idea, dressed up in mathematical clothing that actually works. Now here is where it gets strange again, and I mean this in a deeper way than the first time I said it. If Feynman's formalism is telling us something real, and I believe it is, because the predictions it produces are accurate to 10 significant figures, which is better accuracy than measuring the width of North America to the width of a human hair, then what it's telling us is that the distinction between particle and antiparticle, between matter and antimatter, is not a fundamental distinction. It is a perspective. It is a choice of how you orient yourself relative to the direction of time. The electron is not a fundamentally different thing from the positron. It is the same thing seen from a different temporal angle. And if that's true, if the particle-antiparticle distinction is really just a question of which way time is pointing, then we are looking at something deep about the structure of time itself. Because here's what that implies. It implies that time as a direction, as a thing that points from past to future, and not the other way around, is not built into the fundamental laws. The fundamental laws of quantum electrodynamics are, to an extremely good approximation, time symmetric. Run the equations forward, run them backward. They give you the same physics. The arrow of time, the fact that eggs break but don't spontaneously reassemble, that you remember the past but not the future, that entropy increases, that arrow is not in the microscopic laws. It emerges. It is a statistical thermodynamic feature of how large collections of particles behave, not a fundamental feature of what particles are. And if time doesn't have a built-in direction at the level of individual particles, then forward and backward are not absolute. They are, in some sense, chosen. And if they're chosen, then the distinction between an electron moving forward and a positron moving backward collapses into a single trajectory with a single identity, seen from two different vantage points in time. I want to be honest with you about how far this argument goes and where it starts to become speculation rather than physics. What I've just described, the time symmetry of the fundamental laws, the mathematical equivalence of electrons and positrons in Feynman's formalism that's established physics, that's not controversial. What's more speculative is the jump from that established physics to the claim that there is, in some operationally meaningful sense, only one electron, That jump requires you to accept that the mathematical equivalence is more than a calculational convenience. It requires you to believe that when we say the same particle, different time direction, we are describing the actual metaphysical situation, not just a useful fiction. I have colleagues who would tell you that question is not a scientific question, that it's a philosophical question, a question about interpretation, not about predictions. And they are not entirely wrong, but I think they're being too quick to close the door because there are physical questions that only come into focus if you take the underlying structure seriously. Questions about the nature of identity in quantum mechanics, questions about what information means in a universe where particle and antiparticle are related by time reversal, questions about whether the initial conditions of the universe, including the matter-antimatter asymmetry that bothered Feynman, have an explanation that lives at this level of structure rather than being imposed from outside. Let me tell you about a conversation that changed the way I thought about this. It wasn't with Wheeler. It was with Gerard Hooft, the Dutch physicist who shared the Nobel Prize with Veltman for their work on the renormalizability of gauge theories. Hooft is one of the deepest thinkers in theoretical physics, and he and I have disagreed about a number of things over the years, including things that touch on the black hole information paradox, which is a battle I have told parts of many times and will probably be telling for the rest of my life. But there was a conversation sometime in the late 80s, I think, where Hooft said something that lodged in my brain like a splinter. He said, the question of whether two particles are really identical or whether they just happen to have the same properties is not a question physics can answer from the outside. It can only be answered by the structure of the theory. If the theory says they're identical, they're identical. If the theory says they're distinct, they're distinct. There's no fact of the matter beyond the theory. I've thought about that for 30 years. I still don't know if he's right. Here's why it matters. In quantum mechanics, identical particles don't just look the same, they behave differently from distinguishable particles in ways that have measurable consequences. When you have two electrons in the same system, the fact that they are genuinely identical, not just similar, but identical in the deep quantum mechanical sense, forces the wave function to be antisymmetric under exchange. You swap the two electrons, and the wave function changes sign. That's the Pauli exclusion principle. That's why matter is stable. That's why atoms have the structure they have. That's why the periodic table exists. That's why you are not a formless plasma. The indistinguishability of electrons is not a curiosity. It is the foundation of the structure of matter, and it operates through a mechanism that has no classical analog. There is nothing in classical physics that corresponds to the wave function changing sign when you exchange two particles. That is a purely quantum phenomenon, and it depends absolutely on the particles being not just similar, but genuinely, mathematically, ontologically the same. Now, here is where I want to connect this to something larger, because I think the one electron idea, properly understood, is not just about electrons. It is a window into something about the nature of physical reality that we are still in the early stages of understanding. In the last 20 or 30 years, the thing that has dominated fundamental physics, and I say this having been in the middle of a lot of it, is the relationship between quantum mechanics and space-time, specifically the question of where space-time comes from. We know that general relativity treats space-time as a dynamical entity. It curves, it stretches, it carries energy and momentum, it responds to the presence of matter. We know that quantum mechanics treats the stuff inside space-time particles, fields, interactions as irreducibly probabilistic, as described by wave functions that obey non-local correlations, as exhibiting entanglement that seems to connect distant regions of space in ways that classical physics cannot accommodate. And we know that reconciling those two frameworks is the central unsolved problem of fundamental physics. We've known that for about 100 years. We have not solved it. Anyone who tells you we have solved it is oversimplifying, but there has been progress. And the progress has come, in large part, from taking seriously the idea that information, the information content of physical systems, how that information is stored, how it moves, whether it is ever lost, is not secondary to physics. It is primary. The black hole information paradox, which is the problem that consumed 20 years of my intellectual life and led to the most public and sustained argument I ever had with Stephen Hawking, is at its heart a question about whether information can be destroyed. Hawking said yes. I said no. The argument was not just about black holes. It was about whether the laws of physics are unitary, whether the universe at the deepest level preserves information, or whether there are circumstances under which information simply ceases to exist. I believe the laws are unitary. I believe information is conserved. I believe that the apparent destruction of information in black holes, which Hawking argued for brilliantly and wrongly, is an illusion produced by not taking seriously enough the quantum structure of space-time. And the reason I bring this up is that the question of identical particles, the question of whether electrons are genuinely the same or just effectively the same, is a question about information. If two particles are genuinely identical, there is no information that distinguishes them. There is no fact of the matter about which one is which. And in a universe where information is conserved and physical, that has consequences. It means the universe doesn't track which electron is which because there is nothing to track. The identity is not just a symmetry, it is a statement about the information content of the world. And now I want to tell you something that I find genuinely unsettling. Not in the way that bad news is unsettling, but in the way that a really good problem is unsettling. The kind of thing that wakes you up at 3 in the morning, not with dread, but with that particular urgency that only comes when you know you're close to something you don't yet understand. The picture I've been building, identical particles as excitations of a single underlying field, the particle-antiparticle duality revealed by the Dirac equation, the mathematical coherence of Wheeler's one-electron idea, when you translate it into Feynman's language, the connection between identity and information, this picture is suggestive. It points somewhere, but it doesn't fully arrive, because here is what I don't know and what I don't think anyone knows. What is the electron field? Not what does it do, not what are its properties. What is it? What is a quantum field? Ontologically, what kind of thing is it? When we say the electron is an excitation of the electron field, and that excitation is what we mean by a particle, we have a formalism, we have equations, we have predictions. What we don't have is a picture of what is actually there. This is not a new problem. It's the problem Bohr and Heisenberg and Einstein were fighting about in the 1920s and 30s, before most of you were born, before I was born. What is the wave function? Is it a real physical thing that exists in the world, or is it a calculational tool, a bookkeeping device for tracking probabilities? Bohr said, don't ask what's really there. Ask only what the experiments show. Einstein said, that's not physics. That's giving up. I am closer to Einstein on this one. I think there is something really there. I think the wave function, the field, the underlying structure, it's real. But I can't tell you what real means here. I can't give you a picture you can hold in your head, because the thing we're talking about doesn't live in the 3 dimensions your head is designed to process. It lives in configuration space, or in Hilbert space, or in whatever the right mathematical structure turns out to be. And we don't yet know how to translate between that structure and the lived experience of being a person in a 4-dimensional space-time. That gap between the mathematical structure and the phenomenological picture is where the deepest physics lives, and it's where the one-electron idea lives too. Because Wheeler's question, which sounded like science fiction when he posed it, is really a question about that gap. It's a question about whether the correct ontology of the electron is a single entity threading through time, or a field pervading all of space, or something else that we haven't yet learned to think about. Those 3 descriptions may not be as different as they sound. They may be three different languages for the same thing, or they may not. We don't know. And I mean that literally, I don't know. And I've been thinking about it for a long time. Let me tell you about the moment in my own work when this question became sharpest for me. It was in the context of the black hole wars, the debate with Hawking, and specifically in the development of what I now think of as the complementarity principle for black holes. The argument, in brief, is this. An observer falling into a black hole experiences nothing unusual at the horizon, the event horizon. The point of no return is not a physically marked place in space, and a freely falling observer would cross it without noticing. But an observer staying outside the black hole, watching from a safe distance, sees something completely different. To the outside observer, the infalling observer appears to slow down, to redshift, to eventually freeze at the horizon, and the information they carry appears to be scrambled and re-radiated in the Hawking radiation that the black hole emits. So, two different observers, two completely different descriptions of what happens to the same information. Both descriptions are self-consistent. Both are, within their own frame, correct. And you might think, that's a contradiction. You can't have two contradictory true descriptions of the same event. But here's what I realized, and what took years to persuade my colleagues of. If the two observers can never compare notes, the observer who falls in can never send a message back out, the observer who stays outside can never go in and check. The two descriptions are inaccessible to each other in principle, not just in practice. And in physics, a contradiction that is inaccessible in principle is not a contradiction. It is complementarity. The same principle that Bohr used to reconcile the wave and particle descriptions of quantum systems. Both are true, but no single experiment can reveal both simultaneously, applied now not to momentum and position, but to the entire experience of space-time. What does this have to do with electrons? Everything. Because what complementarity teaches us is that physical reality does not have a single God's eye description that is simultaneously accessible to all observers. Reality is observer-dependent in a deep sense that goes far beyond the relativity of simultaneity that Einstein taught us. And if that's true, then the question, how many electrons are there really, may not have a single answer that is valid for all observers. The outside observer, watching the universe from some particular vantage point in space-time, counts 10 to the 80 electrons. A different observer with a different relationship to the universe's causal structure might count differently. Not because the electrons are in different places, but because the concept of one electron and many electrons is less absolute than we are inclined to believe. I am not claiming this is the resolution. I am claiming this is the right territory to be exploring. I am claiming that Wheeler's insane-sounding idea, one electron, threading through time, becomes less insane the deeper you go into the physics, and that the reason it becomes less insane is not that we found evidence for it in the naive sense, but that we found that the naive objections to it dissolve when you take seriously the quantum mechanical, field theoretic, information theoretic structure of the universe. The matter-antimatter asymmetry is a real problem for the literal version of the idea. I am not pretending otherwise. But the mathematical structure underneath the idea, the Dirac equation, the Feynman formalism, the identity of quantum particles, the relationship between time reversal and antiparticles, that structure is real, it is established, and it is pointing somewhere we haven't fully arrived at yet. I want to say something now about the nature of ideas in physics, because I think it's relevant to how you should hear everything I've just said. There is a category of idea in physics that I think of as a productive wrong idea, an idea that is not literally true, or not true in the way its originator imagined, but that points so directly at something real that it generates good physics for decades. Wheeler was full of these. His idea of geometrodynamics, the attempt to build all of physics out of the geometry of space-time alone, didn't work, not in the way he hoped. But it seeded a generation of thinking about the relationship between geometry and physics that culminated in string theory, in loop quantum gravity, in the holographic principle, in the whole modern project of understanding space-time as an emergent structure rather than a fixed background. Wheeler was wrong in the specific and right in the general. That is a very valuable kind of wrong. I think the one electron universe is in that category. Wrong in the specific. There are not literally 10 to the 80 copies of a single particle tracing a single world line through the history of the cosmos, at least not in any description that solves the matter-antimatter problem. But right in the general, there is something deep about the identity of particles, about the relationship between particles and fields, about the role of time direction in defining what we mean by particle versus antiparticle, about the informational structure of quantum states, that the one electron idea is the first rough sketch of. Wheeler was drawing the outline. The field has been filling it in for 70 years. We're not done. And here is the thing about physics that I have been doing for 50 years and that I want to leave you with, because it is the truest thing I know how to say about this enterprise. The ideas that seem most outrageous are often the ones that are closest to something real. Not always. There are plenty of outrageous ideas that are just wrong. Flat out wrong, not productively wrong, not pointing at anything, just wrong. And you have to be able to tell the difference. That requires knowing the mathematics well enough to check whether the outrageous idea survives contact with the equations and whether the equations it produces survive contact with experiment. Wheeler's idea survives contact with the mathematics in the form of the Feynman formalism. It does not fully survive contact with experiment because of the matter-antimatter asymmetry. But the mathematics that it generated, the mathematics of antiparticles as time-reversed particles, of identical particles as quantum field excitations, of the Pauli exclusion principle as a consequence of genuine identity rather than mere similarity that mathematics does survive. And it survives at extraordinary precision. So let me close with the thing that actually keeps me up at night. Not the matter-antimatter asymmetry. We'll figure that out eventually. Or we won't. And either way, it's not the deepest problem. The deepest problem, the one that connects the one electron idea to everything I've spent the last 20 years thinking about, is this. We don't have a good theory of why the universe has the particular quantum fields it has. We can write down the standard model, which tells you that there are quarks and leptons and gauge bosons and a Higgs field, and we can describe those fields with extraordinary precision, and the description matches experiment better than any other scientific theory ever constructed. But we cannot tell you why those fields and not some others. We cannot tell you why the electron field exists, why it has the mass it has, why it has the charge it has. Those are inputs to the theory. They are not outputs. They are things we measured, not things we derived. And until we have a theory that tells us why the electron field is what it is, a theory that derives the fields from something deeper, something more fundamental, we will not fully understand what we mean when we say the electron is an excitation of a field. We will not know whether Wheeler's intuition is pointing at a real deep structure of the universe, or whether it is a beautiful coincidence that the mathematics of time reversal and the mathematics of antiparticles happen to overlap in a way that makes one electron feel like a coherent idea when it isn't quite. I don't have that theory. Nobody does. String theory is a candidate, and I have spent a significant portion of my life working on it, and I believe it contains real physics. But we have not yet extracted from string theory a derivation of why the electron is what it is. We're working on it. We've been working on it for 40 years. The problem is hard. What I can tell you is this. The question that Wheeler posed, why are all electrons the same, and what does that sameness mean, is not a solved question. It has partial answers. It has beautiful mathematics. It has the Dirac equation and Feynman's diagrams and quantum field theory and all the machinery of the standard model. But the question underneath the question, what is the electron really, and why is it what it is, that question is open. And the fact that it's open is not a failure, it is an invitation. It is physics telling you that there is more to find. Wheeler knew that. He spent his whole life chasing what he called the question behind the question. He never stopped. He was still thinking about it when he died at 96 years old, still restless, still unsatisfied, still asking. That's not a cautionary tale. That's the model. You don't get to be finished. The universe doesn't let you be finished. And if you're doing this right, if you're asking the real questions and not just the tractable ones you shouldn't want to be, one electron, the whole universe, the same particle, over and over, threading through 10 billion years of cosmic history, showing up in your atoms and in the atoms of a star that hasn't formed yet, identical in ways that have no business being so perfect. Maybe that's what's really going on. Maybe it isn't. But the day you stop asking is the day the physics stops.